Good afternoon, everyone. Welcome to the continuing sessions of our CCENT Blitz. Everyone's here trying to get CCENT certified. This is another in our continuing series. Thank you for joining us here, and if you're watching online, thanks for joining us there too. I'm going to talk about IP addressing. There's a lot of topics in IP addressing that we could cover, and some of them are probably more than we need to cover right now. I'm going to talk a little bit about subnetting, but not a lot, because there's another module about subnetting later on. We'll talk about it more then. So let's just talk about IP addressing. And first of all, let's ask, what is an address? Everybody knows addressing. They use them every day. For example, there's an address on your house. Okay? And there are other addresses or numbers, since all we're really talking about is numbers. There's other numbers that you use to identify yourself, like a social security number. But the interesting thing about a social security number is no matter where you go, your number is the same. So it tells who you are, but not where you are. And that's how an IP address is different from a MAC address. If you've ever used a MAC address at layer 2, which we've talked about the different layers in the OSI model and how the information available is used at different layers. The MAC address is at layer 2, and it never changes, kind of like your social security number. So as you move from one location to another, I can positively identify you by that number, but I can't identify your location from that number. That's how an IP address differs from any other kind of address. And you'll hear a lot of people, particularly in the Cisco world, talk about layer 2 address or layer 3 address. The layer 2 address is the MAC address. The layer 3 address is the IP address. And again, let's just think of it as a number. It's nothing more than a number. And also remember that since computers are dealing with these numbers, in reality, they're always binary. A lot of people get confused when we talk about different kinds of addresses, and they'll say, well, how come it's represented in decimal, or if it's IPv6, it's in hexadecimal? Well, really, it's neither one. It's always binary. It's only written in decimal or hexadecimal, so you can understand it more easily. And an IP address, when I say an IP address, unless I say otherwise, I really mean an IP version 4 address, which is a 32-bit number. If I mean an IP version 6 address, I'll say IPv6 or just v6 or something like that, and that's a 128-bit address. We're not going to go into 128-bit addressing, just 32-bit addresses. So if we were to take a 32-bit number and write it in binary, it would look something like this. Just a string of ones and zeros. And unfortunately, we're not really good as human beings at reading a long string, 32 bits of ones and zeros. So what we do is we break it down to make it a little easier for us to read. Now it turns out that the easiest way to break this down is to break it into 4 8-bit sections, because 8 bits makes a byte. Actually, it turns out that 2 bytes makes a word, and 4 bytes makes a double word, and that's an old unit of storage from long before even the internet was widely available, but that's why it happens to be 32-bit. It's not a random number. So if we take that 32-bit address and break it down into 4 8-bit or 1-byte chunks, then we have the possibility of making numbers ranging from this, all zeros, which of course equals 0, or this, all ones, which it turns out equals 255. So all the numbers that we're going to be dealing with in an IP address, and also in the masks that we apply to these addresses, are going to be between 0 and 255. But remember, we have 4 of those numbers. And we separate them by dots. This is sometimes referred to as dotted decimal notation. And again, it's just a convenience, and it helps us read the number. Here's an example of an IP address in dotted decimal notation. 131.161.10.20, and that's how you would read that. Now remember, though, that it's actually being used as a binary number. So if we were to take 131 and write it in binary, it would look like this. Okay, again, a string of ones and zeros. And the same would apply to the entire address. Now I said that the difference between an IP address and a MAC address is that it tells us 2 things. Instead of just who you are, it also tells us where you are. Well, in order to tell us 2 things, it has to be divided into 2 parts, right? Make sense? So the question is, where do I divide it? Originally, when they first began doing this, all IP addresses were divided here. The first 8 bits were used to denote a network location, And all the rest were used to denote hosts within that network. But if you think about it, that isn't a very flexible scheme. Because if I only have 8 bits available for networks, and I can only make a number as large as 255 with 8 bits, that means I can only have 255 networks. Clearly, everyone recognizes that there are more than 255 networks in the internet today. So in order to designate more networks, we need more bits. So we could move over here. We could use 16 bits to denote the network, leaving 16 for the host. And that would give us, disallowing for some of the fixed bits that we'll deal with later, 65,000-ish networks with the same number of hosts per network. And that sounds pretty good. 65,000 is a lot more networks than 255. But it's still not a lot. Even today, that wouldn't be a very large number of networks. But more importantly, it seems almost ridiculous to think of any network that you're going to be associated with actually having 65,000 separate hosts in it. Most of the networks you're going to deal with are pretty small. So we could divide the address here and have 24 bits, or millions of networks, leaving only 8 bits for host, which means each one of those millions of networks would only have 255 available addresses for hosts. Now the real question is, which of those schemes, dividing it here, here, or here, is better? And the correct answer is, it depends. It depends on what you're trying to accomplish when you do this. And it turns out that I like all of those options equally well, depending upon what circumstances I'm trying to address. So I want to be able to do that. I want to be able to divide it here sometimes and produce a very small number of very large networks. I want to be able to divide it here sometimes and produce a relatively large number of networks with a large number of hosts. And sometimes I want to divide it here, producing a very large number of networks that have, admittedly, a relatively small number of hosts within them. Now this raises the problem that you need to know which of these schemes I'm using. So if I send you a packet with an IP address in it, you need to be able to tell instantly which of these address schemes I'm using, which bits I believe identify my network, and which ones identify hosts within my network. Now the way I do that is I follow, as you've heard in earlier videos, a standard. And the standard is pretty simple. Now you got to remember that this was actually developed in the 70s and deployed in the 80s, and computers then probably had less computational power than my telephone, and probably were as big as this room and generated enough heat to heat the building. So they didn't have time or the ability to do a lot of processing to make this decision. And actually, I can make this decision. I can send you my decision embedded in the address by examining, most people would say 3, but actually I only need to examine 2 bits to figure out how I'm going to divide my address. Now, if we start looking at binary numbers, and we're really only going to look at this segment, and when you think of a segment in an IP address, a nice way to refer to it is an octet, because it represents 8 bits. So I'm going to talk about the first octet, the second octet, third, and fourth octet. Each one of them is 8 bits. So let's take this one octet here, the first one. And I'm going to tell you now that we're going to use that octet to determine the scheme of each IP address. And we're going to refer to those different schemes as different classes of address. All right? So let's just say that we started out by saying the first bit of the octet had to be a 0. Okay? If that's true, then if we know anything at all about binary, and let's put this on the board, we know that we start with 1. The first bit in a binary string has the value of 1, and as we move to the left, every value is doubled. So this is 2, 4, 8, 16, 32, 64, and 128. And you can think of this as a light switch. If the switch is off, the value is not added into the total. If the switch is on, it is. 0 denotes off, and 1 denotes on. So if I had a string of just 2 bits and it was 0, 1, its value would be 1. But if it was the other way around, like that, its value would be 2. Or, if this was a 1, it would be 3. It would be the sum of both of those because they're on. Now, let's take a look here. And I said that this first bit here has the value of 128. And that in 8 bits, the largest number you could make is 255. So if I were to subtract 128 from 255, I'd get 127. Okay? That means that if I leave this bit off, if I don't turn it on, in 8 bits, the largest number I can make is 127. So I can tell you right now, if the first bit is a 0, all the numbers in that range are going to be between 0 and 127. Okay? Now let's change that a little bit. And let's say that the first bit is a 1, and the second bit is a 0.